Okay, so we're ready for the talk. So it's kind of on time. So let me find your introduction. Yeah, and don't be nervous. Yeah, so a free talk. So it's your talk show.
Awesome.
Okay, I will start now. So David, yeah. Uh, okay. Good morning, everyone. So today we are very happy to have Dr. David Stephen. He's now working at Quantinuum in US. So first of all, so let me give a very brief intro of Dr. Of David. Uh, so he graduated with a master degree from UBC, Professor Robert Rosendorf, who is an expert on the MBQC, which is measurement-based quantum computing, and then PhD from the Max Planck Institute with Dr. Norbert Schuch in Germany. And then he did a postdoc at the University of Colorado at Boulder and Caltech, right? So, and he has worked on many different things, from MBQC to quantum algorithm, many-body physics, and also now he's interested in like quantum state generation and circular compilations. Okay. Today, so David is happy to share with us on some work related to MBQC, right? Yeah. So, yeah, okay, I will leave the rest time to David. Okay.
Okay, thanks a lot for the intro. I'll share my screen and get started. Is that looking good?
Yeah. So full screen?
Yeah, it should be full screen now.
Yeah. Good.
Okay. Yeah, please let me know if something's wrong. But I'll get started. Um, so yeah, it's my pleasure to talk to everyone and share some work I did. So as Dongxing said, I just started at Quantinuum recently, which is a company based in Broomfield in the U.S. But before that, I was doing this postdoc at Boulder and Caltech, and these are two papers that kind of came out of that. So this talk will be about this first paper with Wenwei, Tsuchi, Robert, and Ruben, and then another one that was kind of a follow-up with Isaac, Maxime, and Hendrik. And it's kind of discussing a new kind of quantum computation, a new way to do quantum circuits, which ends up you have to deal with very unusual gate sets, and it's about the challenges of dealing with those gate sets and the opportunities. And actually, this picture on the first slide is actually a picture of a gate set, believe it or not, and I love it because it looks like a computer chip kind of, and it actually does represent a scheme of quantum computation. So I won't actually show this picture again, but if anyone has questions at the end, I can talk more. So let me get started. And so this talk is some of the context is about universal gate sets. And what do we mean by a universal gate set? We just mean a set of quantum gates which can generate any quantum circuit or which can generate any unitary transformation by combining these gates, either approximately or exactly. And if I asked you to think of a universal gate set, probably you might think of something like a gate set with the Hadamard matrix, or the Hadamard gate, which is a single qubit gate, maybe a C0 gate, which is a 2-qubit gate, and then the T gate. You might think kind of more device-minded, think of some kind of physical Ising interaction with some kind of single qubit gate you can do, or maybe something like Hadamard and Toffoli. And as we know, there are lots of universal gate sets. In fact, there's infinitely many. But most of the gate sets which you would think of, including all of these, have the property that they kind of have this local translationally variant structure. And what I mean by that is when I say I have a Hadamard and a Toffoli, I mean that I can really act with Hadamard on any of my qubits and Toffoli, which is a 3-qubit gate, on any 3 of my qubits. So I'm kind of saying these small gates I have, but I'm able to put them anywhere I want. So that's what I mean by, you have these little local gates and you can kind of push them anywhere you want in your circuit. That's kind of what I mean by this local translationally invariant structure. And this is a very natural structure to have. That's kind of what we mean by a gate, is kind of an elementary piece that you stick together to make a circuit. But what about gate sets that don't look like this? Where do they come up? What do they look like? And how can we use them? So let me just give a first taste of when these kinds of gate sets would come up. So when would we want to consider gate sets that have a different form? Well, one example was given in this paper by my old supervisor, Robert Rossendorf, back in 2005. And there he considered a gate set which has these two kind of operations. And what this looks like is kind of a simultaneous interaction between all pairs of neighboring qubits on a line all at once. And this looks like you do a single qubit rotation, but you do it to all of your qubits all at once. Okay, so I don't have the power to ever address one qubit at a time. I have to address all my qubits all at once. Those are my only gates. And this might be motivated by like a physical architecture where, say, you have some line of atoms and you can shine a laser beam through all of them. But by doing that, you cause all of them to interact all at once. And so you don't really have this local control. So this gate set was actually shown by Robert to be universal, meaning by combining these kinds of gates, you can do any operation, even though you have this kind of uniformity constraint. And so here so this kind of goes beyond this local structure I talked about in the previous slide, and here it's due to maybe a physical constraint of your architecture. Another example comes when you consider quantum error correction codes. And that's because in quantum error correction codes, there are certain gates that are easy to do and certain gates that are hard to do. And sometimes the class of easy gates is called transversal gates. And when you have these kind of high rate codes, so codes which kind of encode many logical qubits inside of some number of physical qubits, the kind of easy gates you get out might not look very nice. So this is just some gate I took from this paper. And here it's saying the gate you can do is kind of some mess of 2-qubit operations, these controlled Zs, on some subset of your qubits. And so you're not able to apply this, any logical gates to any pair of qubits that you want. You just kind of have this one big mess of gates, and that's what you can do. And so you don't and so you can say, well, what can we do with this? Can we work with this? Can we make this universal? And maybe a final example is something more generic. In fault tolerance, a very common circuit architecture to consider is something called Clifford plus T circuits, where you have these Clifford gates, which here are all the orange gates, and also these T gates, which are here, which this here is like a pi/8 rotation about the z-axis. And this would be a standard circuit you would write down. Again, you have the kind of these local blocks that you're building together. But what you can do in this structure is you can take all the Clifford gates and pull them to the right of your circuit. And Clifford gates have a special property that when they encounter a rotation like this, they just turn it into a different rotation. So this Z pi/8 rotation might become something like a 4-body Z, 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 Y pi/8 rotation, and so on. But when I do this, kind of all the Clifford gates they kind of get pushed to the right and they get absorbed by the measurements. And so here you are left with these gates, which look like big rotations or big kind of non-local rotations. And so this is something you can always do when you have a Clifford circuit. And if you were just given this circuit on the right, you can ask, what are different ways I can decompose it into the gates I have? And of course, on the left, this is one answer, but there might be other answers that are more efficient depending on what operations you can naturally do. Okay, but the context that I want to focus more on is measurement-based quantum computation. And I'm not going to explain how this works. I'm just going to say the result of what happens So what happens in measurement-based quantum computation is it's very different from the normal circuit model. What you start with is some 2D grid of qubits, and they start off in some entangled state. Then once you're given that state, all you do from that point on is make measurements, single qubit measurements of all the qubits in your state in some basis. And so here, these colors here represent different measurement bases. You don't have to think too much about what they mean, but I'm just saying you have this two-dimensional entangled state and you measure it in different bases. The remarkable thing is that by doing this, you can effectively simulate quantum circuits. So I've kind of drawn this circuit here to be what this MBQC might implement. And what kind of happens is these Z measurements kind of carve out a structure of your circuit. And then you're left with kind of these 3 horizontal lines of qubits. So that turns into the 3 qubits in my circuit. And whenever these lines are connected, that gives you an entangling gate and so on. So I'm not going to talk at all about how this works. I just want to say that by doing these measurements on these entangled states, which are called cluster states, you can efficiently implement quantum circuits. And the quantum circuits that you implement are exactly the kind I talked about on the first slide. You have kind of local entangling gates, local single qubit gates, and you can apply them freely to any qubits that you want. And so this very naturally translates circuits into the MBQC and back and forth. So this MBQC was invented back in 2003 by Robert Rossendorf and his supervisor Hans Briegel. And well, it really was a huge new paradigm for quantum computation that's led to many insights. It led to a completely new way of looking at fault tolerance and quantum error correction, and many, many more things. I could go on about all the things MBQC has given us. But what I want to talk about now is that it turns out there are other ways to take this two-dimensional entangled state, this cluster state. There are other ways you can measure it and still get out a universal quantum computation. For example, it was shown in this paper in 2017 that you can get rid of these Z measurements. And so now I have this cluster state, and the only measurements I can do are measurements kind of in the XY plane, so X, Y, or some rotated basis in that plane. And what happens now is the kind of circuits that I simulate by doing this have the structure where at every time step I have these entangling gates happening between all of my qubits all at once. So I have all these entangling gates at every time step, and so here's 2 time steps. And what I'm able to do is by choosing my measurement bases, I can insert these theta here, which represent single qubit Z rotations. But that's all I can do. So I cannot control the placement of these entangling operations or these Hadamard gates. They just happen every time step automatically. All I can do is choose when to insert these Z rotations. This is kind of reminiscent of the example I gave on the previous slide, where every time you have entanglement everywhere. And so this turns out to still be universal. Again, I'm not going to say why, but I will talk about something similar shortly. And it's not just, maybe it's kind of conceptually interesting that you can get rid of the Z measurements, but this was also practically useful. For example, there's a scheme of quantum computation called blind quantum computation, where you're able to tell someone who has a quantum computer what you want them to do, and they will do it, but they don't actually know what circuit you ran. So it kind of gives you some security. And also with some work that we did in the past, it enabled us to find something that was called a computationally universal phase of matter. But I won't get into more detail about that. But both of these results require the ability to get rid of these Z measurements. And yeah. But the example I'm going to focus on for the talk is something even more restricted that looks like this, where again, I have a 2D cluster state, but almost all of the qubits I have to measure in the Y basis. I don't have any choice. I have to measure them in the Y basis. And the only control I have is how I measure the qubits on the top row. And those I can measure in the XY plane. So I have choice, so I have control over that angle of measurement. And similar to this previous one, the kind of circuits that you can implement by doing this measurement pattern look like this, where every time step I have all these entangling gates, some single qubit gates, and now my only degree of control is to insert these rotations on the first qubit. And I'm going to tell you shortly about how this actually is still universal. And so, as I'll say and of course, not only is this kind of just a fun curiosity, it also enables some new results, like the previous case. For example, I'll talk about how this enables a way to do measurement-based quantum computation in a one-dimensional architecture. And then I'm going to move into kind of a more vague discussion about how it kind of gives you a more efficient way of using certain quantum resources, namely these so-called T-gates.
Hi, David.
Yep.
I have a question. So the measurement now, they should also be classically ordered, right? You need to feed forward the result, right?
Exactly. So in general, in measurement-based quantum computation, you not only have to choose your measurement bases to do the algorithm you want, but you also have to adapt them on the fly based off the measurement outcomes you got previously. Over on the right side here, actually the Y measurements do not need to be done adaptively at all. And as I'll talk about on the next slide, you can do them all at the very start. But the rotations on the top row still need to be done adaptively. That's correct.
Okay, so from left to right, right?
From left to right, yes.
Yeah. Okay.
Thanks. So let me zoom in on this case again. So again, you could ask, why would I consider this strange constraint on my measurement bases, where all I can do is, or where I have to measure almost all the qubits in the Y basis, and I only have control over the first row. And the reason is what we explored in a paper is that, like I just said, when you want to use the state, you can do all of the Y measurements at the start, and then you're just left with some row of qubits on the top, and those are your unmeasured qubits. And after you've done all these Y measurements, these qubits are in some entangled state. And there's a different way of obtaining that same entangled state, which looks like this, where rather than taking a 2D state and measuring a bunch of the qubits, I just have a 1D state, and I evolve it over some deep circuit where the depth of this circuit is kind of the same as the height of this 2D state over here. So if I take these initial product state and evolve it by the circuit, I end up with some entangled state on a 1D line, and that turns out to be the exact same entangled state that I end up with over here. Okay, so kind of these two states are the same, and I can either get it from preparing this 2D state and doing a bunch of measurements, or I can get it purely in a 1D architecture. So here I'm kind of trading one spatial dimension for time in some sense. And the reason this is interesting is because, as I'm going to show you shortly, this measurement pattern on the left is universal, which means that if I'm able to prepare this 1D state, it is universal for measurement-based quantum computation, meaning by choosing the basis of my measurement, I can efficiently implement any quantum circuit. And so the reason this is interesting in this case is because on the right-hand side, I have a state that was prepared purely in a one-dimensional architecture. And it was very commonly believed until this work that you cannot have universal measurement-based quantum computation in the one-dimensional architecture. Now, of course, the reason we got over that belief is this very crucial modification that the depth of the circuit we need to create our resource state has to grow with the number of logical qubits we want. But and that's how we get around, or that's how we're able to fit universal MBQC in one dimension. But yeah, so this is the subject of this paper, but I'm not going to say much more about this one dimensional result. What I do want to talk about is how the heck is this circuit universal? So like I said, by measuring these resource states, either the one that you are either prepared in 2D or 1D, it doesn't matter. But by measuring it, the kind of quantum circuit I'm able to implement looks like this. So these are the circuits that we're going to be dealing with, where what we have is this box, which consists of a bunch of entangling gates and single qubit gates. And then we have single qubit Z rotations of the first qubit. And those are the only two gates we have, and they just repeat over and over again. And the only degree of freedom we have is choosing these angles of the measurements on the top row. Of these gates on the top row. Yeah. Again, I'm going to not be thinking about measurement-based quantum computation anymore. I'm just saying this is the kind of circuit we're able to implement. Let's study this circuit. And so I'm claiming that this is a universal structure In fact, we were able to prove this theorem, which is circuits of this form are universal, not quite on all k of your logical qubits, but on approximately 3/4 of them, so just some constant overhead. And moreover, you can kind of simulate kind of the local gates if you wanted to with the most polynomial overhead. But I'm going to try to argue that you don't just want to reduce to the standard gate set. But yeah, this I think is quite remarkable that this gate set is universal, because on one hand, you only really have direct control over the first qubit. All of the gates that touch the other qubits are just kind of this fixed block that you can't control. So how can you possibly selectively control, say, the fourth qubit? And I will explain how that works. But also fundamentally, another interesting thing about this structure is that all the gates in this dotted box are again these so-called Clifford operators that I told you about earlier, where these Clifford operators are a certain subset of quantum gates that, in some sense, in an error correction context, are very easy to implement. And so the only non-Clifford operations you ever have to do are these Z rotations. And so you kind of only have to do the hard work to do non-Clifford operations on this first qubit. And this meshes very well with a proposed structure by Abomben some years ago, where you kind of come up with some error correcting code where most of your qubits are encoded in some two-dimensional code, and that allows you to do these Clifford operations easily. And then only this qubit at the top is encoded in a more complicated code, which allows you to do these non-Clifford rotations. And so this structure really meshes well with this. Maybe another interest. Yeah.
So is the theorem a asymptotic result, or does it work for small p?
It works for all k.
So do you know where are those effective qubits? Say here, in the figure there are 5 qubits. Do you know which one works?
Yes, you're basically going to ignore every fourth qubit. And so if you just kind of start with that, with every fourth qubit in like a fixed state, it's going to like stay in that state forever. Nothing interesting is going to happen to it. But then the rest of the qubits you can do a universal gate set on them. And so it's very easy to see the encoding. It's just a subset of your qubits.
Okay, interesting.
Maybe a final remark about the structures, again, about in this fault-tolerant context, normally for universality, you want to do some large number of Clifford gates in order to be able to have a universal circuit. But if we treat this big dotted box as one Clifford gate, it's just one unitary matrix, and I'm not even allowing it to be permuted or acting on different qubits, just one matrix. This one Clifford matrix is all you need for your Clifford gates. So if you ask the question, how many Clifford gates do I need to make universal quantum computation? The answer is 1, which I think is kind of interesting. Okay, let me talk about how we see that this circuit is universal, and that's going to lead into the second part of my talk. So again, I talked about this conundrum of how we're only able to directly control the first qubit. How do we control the others? And the idea looks something like this. So for k equals 1, remember I have this parameter k, which is the number of qubits I have. For k equals 1, my circuits look like this, where I have my Z rotations, and now this dotted box is just this single qubit gate, which is the Hadamard times the phase gate, and then a Z rotation, and this repeats. I can manipulate this circuit in the following way. If I pull all of these Hadamard S gates to the right-hand side, they cancel out because HS cubed is the identity. And as I pull them past these rotations turn into different kinds of rotations. So we have this Z rotation becomes a Y rotation, and this one becomes an X rotation. And so this block of gates is equivalent to doing a Z rotation, then a Y rotation, then an X rotation. And so if we look at one qubit, if we look at ignore this line of qubits up here. This is more for the measurement-based context. But if we look at what our computation looks like, it looks like a repeating cycle of a Z rotation, a Y rotation, an X rotation, Z, Y, X, and so on. And this repeats over and over again. And that's what the kind of circuit that we're able to do looks like. And we're able to choose these angles of rotation. And we know that if we can do a Z rotation and a Y rotation and an X rotation, we can combine these to do any rotation of our single qubit. So this is a universal structure, a universal gate set for one qubit. Now we can play the same game for more qubits, but something interesting happens. And we get the same effect where kind of our rotations change over time. And what we have is the first kind of Z rotation stays as a Z rotation of the first logical qubit. And so now I have 3 rows of this table corresponding to my 3 qubits. And each column is telling me about a kind of gate I can do. So the first kind of gate I can do is a Z rotation of the first qubit. The second kind of gate I can do is a 2-qubit rotation. It's a YZ rotation of the first 2 qubits. Then I get a YXZ rotation of all 3 qubits, and so on. So each row is a qubit in this picture, and each column represents a different kind of quantum gate I can do on these qubits. Okay, and this is exactly the same argument I had before. It's just taking this structure and pulling these dotted boxes all the way to the right of my circuit. Then I'm left with a bunch of rotations by different Pauli operators, and that's what these tables are. And so you can ask the same question. By combining all of these different kinds of rotations, can I do any unitary I want on my 3 qubits? And as we increase the number of qubits, we get more rows to the table, and we get more operations we can do. And we actually get this interesting fractal pattern appearing in these gates. And this is going to be important for how we actually prove the universality. So we have a scheme of quantum computation which looks much different from normal quantum computation, in that our elementary gates we can do are these big many-body Pauli rotations. So for example, in this k equals 31 case, one of the gates I can do is a big y, z, 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 x, y, 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 z, z, some big, multi-qubit rotation. So it's not like I have these small building blocks anymore. And furthermore, every time I increase the number of qubits I have, my gate set is different. It's not like I'm just, it doesn't just, add on more small gates. My gate set is completely different for every number of qubits. So how do I deal with this kind of circuit? And so this is kind of the transition point where I'm going to go into the second part of my talk, which is about the second paper, which was me trying to answer this question: how do I deal with these kinds of gates? And so let me state the question more generally: is if I have a set of Pauli rotations, which again is something like e to the I theta times a Pauli string, when does this generate all unitary operations? And so the key fact to analyze this is the fact that by taking 2 of these rotations, we can sometimes generate a new one. And this is based on this following equation. If I can do a rotation about some Pauli string Q and a Pauli string P, then by combining them in this way, if I can get a rotation about the commutator of P and Q, if they anti-commute, because if they commute, the commutator is just 0. So for example, if I can do a Z rotation and an X rotation in one qubit, by combining them, I can do a Y rotation. And so this reproduces kind of a well-known fact that if you want to do universal computation on a single qubit, you only need to be able to do X rotations and Z rotations natively, because by combining these, you can get Y rotations. But again, it's very important that X and Z anti-commute. That's why this was able to work. For example, if I could do an XX rotation on 2 qubits and a ZZ rotation, I cannot combine them in this way to get a YY rotation, because XX and ZZ commute with each other. So I can only play this game of getting new rotations if I have 2 Paulis that anti-commute. And so what we're going to say is that if we have a set of Pauli rotations that we can do, we'll say it's universal if all Paulis can be generated by using these commutators. So by taking commutators over and over again of my generating set, can I generate all Pauli operators? This is a necessary and sufficient condition for this set of gates to be universal. So one example of one standard example of a universal set is what I would call the standard gate set, where the rotations I'm able to do are X rotations and Z rotations of every qubit, and also ZZ rotations of neighboring qubits. So this is kind of exactly the standard gate set. You have single qubit gates and one entanglement gate. And so this is universal. And so you can indeed check that by taking commutators of these operators, you can generate all Paulis. For example, if I take a commutator of Z1, Z2 with X2, so I combine the gates in this way, I can get a rotation about Z1, Y2. And if I take this guy again and take a commutator with Z2, Z3, I can get a rotation ZXZ on 3 qubits. And so you can kind of imagine by combining all these gates, I can build up any Pauli string I want. And that's what I need for universality. So this is the question we need to answer for the set of Paulis that I gave you before. And remember, every column here represents one Pauli operator. So can we take commutators of these Paulis and generate all Pauli operators by doing that? That's kind of the game we have to play. And furthermore, we would like to, be able to do this efficiently. Namely, if there's some Pauli we want to generate, how can we efficiently find the sequence of commutators we need to get at? And how long does the sequence need to be? These are some of the questions I'm going to address. And so let me talk about a generic way to approach this. And a generic way of doing this is you kind of just build, by brute force, you build a tree of all possible commutators you can do, all sequences of commutators. And you see eventually, does every Pauli operator appear in this tree or not? If it does, you have a universal gate set. If it doesn't, then you don't. So the way this tree works is we'll start with one Pauli operator, say P1, which again, back in the previous context, will be one column of these tables I'm drawing. And then I consider the commutator of P1 with all the other generators, P2 through Pn. Some of these commutators will be 0, but some of them will be non-zero, and that will give me a new Pauli. So then from that one, I can take a commutator of that again with another generator, and I can look at all generators. And again, some of them will be 0, some of them will be non-zero. And we might also get some repeats in this tree. And so if we find a Pauli here that we already found it at a previous layer, we just kind of ignore it. And if we ever get to a layer of this tree where we don't generate any new Pauli operators, we know that we're finished. We found every possible Pauli that we can generate using commutators. And if by that point we found all Paulis, then it's universal. So this tree construction always works, and it completely determines the algebra. And by algebra, I just mean the set of Pauli operators that you can generate. And it also gives you like an optimal sequence to realize any Pauli in the algebra. Because if I want to do some Pauli, I find it in the tree, and then I trace that tree back to the top, and that will give me a sequence of Pauli commutators, or a sequence of commutators to take to realize that. Unfortunately, generating this tree is exponentially costly because there's exponentially many Paulis, exponential in the number of qubits, and so it's completely infeasible to generate this tree once you get beyond, say, 20 qubits. So we need to ask, is there a way to kind of check for universality without building this tree? Is there a way to find efficient sequences to generate Paulis without building this tree? Another question I'm going to address is, what is the minimal set of Paulis that you start with, such that this tree will contain all Paulis, meaning the minimal set, kind of the minimal generating set of Paulis that generates all Paulis? What is the size of that set? And finally, how quickly are the Paulis generated, which is kind of how deep does this tree need to go until you've found all Pauli operators? So these are the kinds of questions we address in the second paper, and I'm going to talk more about that.
Oh, hi, David. Yeah. So this is interesting. But meanwhile, do we also need different angles for the rotation?
Yeah. So I'm assuming we can do arbitrary angles of rotations, but in the standard kind of Solovay-Kitaev sense, this will still work as long as we can do kind of some dense subset angles.
Yeah. Great.
But
Also, the circuit structure it is a QCA, right? Automata, right?
Yeah. The dotted box was a QCA, and so what these plots are is kind of taking Z1 and evolving it by a QCA, and this gives me all of my generating set of Paulis.
Yeah. Okay.
So let me quickly answer these questions for the case of this gate set that I showed you, which again for every number of qubits, we come up with one of these plots. Every column is a different Pauli operator. And so for every number of qubits, we have to answer this question from scratch. Do all of these columns generate all Paulis or not? So using brute force, by building this tree, you can show that for k equals 3, it is universal. Namely, by taking commutators of these Paulis, I can generate all Paulis. Therefore, this is a universal gate set. And now I'm not going to go into much more detail of the proof, but what I want to show you is that this kind of, because of this fractal structure of this plot, this repeating structure, if you look at the operators contained in this red box, they kind of repeat over many length scales. So they kind of repeat at all at all qubit numbers, not quite length scales, but kind of at all positions. And what we're able to show is that kind of this is enough to give universality for all k. And this is not straightforward because, yes, I have what looks like my universal set here, but it also comes with all this junk up here acting on the previous qubits. And so it's not at all obvious that this leads to universality, but we were able to leverage the structure and turn it into a proof. And the full proof is, this set of Paulis is universal for all k, meaning I can find a sequence of commutators to get any Pauli. And furthermore, there exists an algorithm which has polynomial complexity, which finds me a sequence of commutators to realize a given Pauli operator. So if I want to find, how do I generate a rotation about some random Pauli string, Z6, I don't have to build this whole tree until I find Z6. There's an efficient algorithm to find that sequence. And furthermore, these sequences are short. They only need to be length, which they only need to be a length which is of order k, which is your number of qubits. And we prove that this length is kind of optimal in scaling. And so, for this, so this is kind of how we prove that this gate set is universal, is we come up with a constructive way to generate all Pauli strings using these generating Paulis. And let me give you an example of what the algorithm looks like. So let's kind of play the game of given a target Pauli, output a sequence of generators that finds it. So here's my first example. Suppose the kind of generating set I have looks like this. So I have 3 qubits. I have ZIZ, XXX, XYY, and YII. This set turns out to not be universal, but it doesn't matter for this argument. And let's say I want to find, I want to decompose the Pauli IXY as a sequence of commutators of these guys. The first step, which is easy to do, is you first write IXY as a product of these Paulis. And to do this, this is just kind of solving a matrix. It's just row reduction. It's very simple to do, and it's efficient. It has polynomial runtime. And it's very easy to see that IXY is equal to the product of these 3 Paulis from my generating set. However, I'm not allowed to take products. I'm only allowed to take commutator, remember. And if I try to take the commutator of ZIZ with XYY, I get 0 because they commute. So instead, I have to first take the commutator of YII with ZIZ because they anti-commute. And then I can take the commutator with XYY. And this will give me something proportional to this product. And so this will give me the Pauli I want. So in this case, I just need to find the right order of sticking all of these Paulis that I want together with commutators. But it's not always that simple. Because imagine this second case here of ZII. Again, it's easy to show that it is a product of these 3 Paulis from my generating set. However, you'll notice that all of these Paulis pairwise commute. So there's no way I can take a commutator of these guys to generate something new. So what I need to do is I need to introduce what I call a helper Pauli, which is this YII, which is going to help facilitate the commutators, and then later I have to get rid of it. So if I start with a commutator of YII and ZIZ, those commute, so that's valid. Then I can tack on XXX and XYY, and then at the end I kind of get rid of this YII. And again, the sequence of commutators effectively gives me the product of all these operators, which is the Pauli I want, because the YII appears twice, so it cancels out. And so this is kind of actually the way we prove the universality that I showed you on the previous slide. We basically show that this algorithm or this way of finding these sequences always works, and therefore we can generate any poly. And again, this is an efficient. Okay, so the next question I want to answer, which I talked about before, is what is the minimal number of polys that generates all polys using commutators? So this is maybe just kind of a fun question, but there will be some utility I'll talk about at the end. So note that our set has size 2k plus 1. On k qubits, we have 2k plus 1 polys, and that's enough to generate all of them. And just as a side note, there's more than 2k plus 1 columns here, and k is 3, but we actually don't use all of the columns in the proof. We only use a subset of them, and the size of that subset is 2k plus 1. So we know the minimal number of polys is no greater than 2k plus 1. And furthermore, we also definitely need at least 2k of them, because otherwise they will never even form a basis. Because if we want it to be possible to obtain any poly by taking commutators of polys, remember the commutator just gives you the product if they anticommute, and it does nothing if they commute. So it's kind of strictly weaker than the product. And so if I can't obtain all polys by taking products of my generators, I certainly can't obtain all polys by taking commutators. And if I want to obtain all by taking products, I need at least 2k of them, because that's kind of the dimension of a basis of the set of polys. And so what we're able to prove is that 2k is not enough. If you ever have a set of 2k polys, there's always at least one poly operator which you cannot generate using commutators, and so it's not universal. Therefore, thanks to our explicit example of size 2k plus 1, 2k plus 1 is the minimal size. And we came up with some other minimal sets. This one kind of has these long Jordan-Wigner strings, kind of X, and then a string of Y, and then Z. This one only consists of 1 and 2 body polys. But yeah, I won't talk about this in more detail. Okay, so the last question I want to address in this context is, do all universal sets of polys generate polys equally quickly? Which is basically saying, if I have a set of generators such that this tree I talked about contains all polys in it, and I have another one which also satisfies that property, are both of those trees the same depth? If I want to get a certain poly, how long does that sequence of commutators need to be to find that? And it turns out the answer is no. And so here are two examples. The two examples are our gate set, the one I've been talking about the whole time, coming from this measurement-based scheme with these cool fractal plots. And the other one is the standard gate set, which, remember, I told you consists of X on all qubits, Z on all qubits, and ZZ on neighboring qubits. Both of these are universal sets, meaning I can generate all polys using commutators. But it turns out that ours generates it more quickly, and that's what this plot is showing. So here this is saying, by the time I've taken a commutators up to a certain length, what fraction of polys have I generated? And so for ours, you need about 20-something polys, or a sequence of length 20-something until you've generated all polys. For the standard gate set, you need a sequence of 40-something, maybe even 50. And furthermore, by the time that our gate set has generated everything, the standard gate set has barely even gotten off the ground. And so we see that the maximum sequence length you need is about 2 times shorter for our gate set than the standard gate set. The average sequence length is about 3 times shorter. So how can we understand this? How can we understand this effect that certain universal sets generate more quickly? And I just want to step back for a second and say, what does this really mean? Because we started talking about gates, and now we're talking about just these polys. What does this mean? What this is saying is that it's possible to have 2 universal gate sets such that one of them fills the space of n-qubit unitaries more quickly than the other. Okay, so this is kind of saying, if we consider a gate set, like our gate set, which has these big weird polystring notations, versus the standard gate set, we can expect on average that we will need fewer gates to reach the unitary that we desire. So we were able to come up with a theory which explains why some sets generate all gates, generate all unitaries more quickly than others. And it's based on kind of the amount of anticommutation amongst your generators. So let's imagine we have a generating set of Paulis such that each element anticommutes with a constant fraction f of the others. So as you know, like true physicists, let's consider the two examples. First, if all of the generators commute with each other, which means f equals 0, clearly our tree is not going to generate all Paulis. And that's because I start with one Pauli and I try to take commutators, but they're all 0. And so I find nothing. And so my process truncates at the first step and I'm done. There's no way I'm universal. So we say, okay, clearly we want some anti-commutation. So let's imagine that all of the generators pairwise anti-commute. So then we have our one Pauli. We consider all of these commutators, and now all of them are non-zero because all of our generators anti-commute. So yay, we've generated a bunch of things really quickly. But now we get to the third step, and we see that because you know Pn anti-commutes with P1 and P2, this commutator is going to be 0. And so now at the second step of the tree, everything is suddenly 0. The process dies, and we're not universal. So clearly, we don't want too little. We don't want too much anti-commutation. We want something that's just right, something in between. So you might reasonably conjecture maybe 1/2 is the optimal. Maybe the optimal gate set has every generator anti-commuting with half of the others. So let's check this by making this argument a bit more precise. So this is just kind of like a combinatorics argument. And actually, I don't want to go into the details for sake of time, but we just can kind of estimate, given this fraction, that every generator anti-commutes with a certain fraction of others. We can estimate how big we expect, or like kind of how many new operators we expect to find by a certain layer of this tree. And it has this functional form where here f here is appearing, f here is this anti-commutation fraction that I talked about. And so this is saying kind of the size of the tree at step r plus 1 has this form, and this form looks like this because this function is actually a famous function in combinatorics. It's called the Q-Pochhammer symbol, and so you can plot it, and it looks like this. And so we see what we expect, which is when the anti-commutation fraction is very low, then our gates, then our kind of algebra, our tree is growing very slowly. On the other hand, when the anti-commutation rate is very high, the tree also grows very slowly. So somewhere in the middle, we have the best rate, and surprisingly, it's not at 0.5, it's around 0.7. And actually, because I said this is a known function, you can go into the online encyclopedia of integer sequences and you can find an exact expression. I guess it's not exact, it's some finite string of numbers, but you know this is a known value, the value at which this function has a maximum. And we find that we kind of have maximal efficiency when this anti-commutation fraction is around 0.706. So if you want to generate all gates as fast as possible, you want all of your generators to anti-commute with approximately 70% of the other generators. So this is kind of like a universal number, which is a very interesting and surprising result, in my opinion, for like a very simple problem of just Pauli strings. And so this is just a very simple-minded combinatorics argument. Does it actually work in practice? So what we did was we randomly generated sets of Paulis with which have a certain anti-commutation fraction amongst them. So we kind of have some random set of Pauli operators such that every one anti-commutes with some fraction of the others. And we generate these, and if you generate these randomly, every once in a while, you'll find a set which is universal. So it generates all Paulis. And so we get a big collection of these. And we look at, starting with this set, how many new Pauli operators have we generated after 5 rounds of commutators, okay? And then it looks like this. And it fits so amazingly well. I was so amazed that this simple argument works so well. So this is kind of really so each one of these dots is a random set of polys, and I'm showing its anti-commutation fraction on the x-axis, and basically how quickly is it generating polys on the y-axis, and it fits this plot extremely well. So finally, let's try to use this argument to explain what we saw previously, which is that our gate set generates faster than the standard gate set, and we can do that in this way. So our gate set turns out that every generator anti-commutes with approximately half of the others, which is pretty high up on this curve. It's not quite optimal, but it's pretty close to optimal. Whereas for the standard gate set, it's very easy to see that every generator only anti-commutes with a constant number of other ones. So the fraction actually goes to 0 as n goes to infinity. Because you can see here, like, Zi only anti-commutes with Xi. So it only anti-commutes with one other poly, as opposed to in our gate set, every generator anti-commutes with half of the others. And so that explains why our gate set, it generates polys so much faster than the standard gate set. And for fun, we can look at the other two examples that I mentioned at some point. And this example 2 here also kind of fits well on this plot. This example 1 does not fit on the plot. And the reason for that is because for this whole argument, I've been assuming that this anti-commutation fraction is kind of uniform amongst all generators. But this set has the property that some of the generators anti-commute with kind of a constant number of the others, like the standard gate set, but some of them anti-commute with kind of a large fraction of the others. And so this anti-commutation fraction is very non-uniform, and that's why it doesn't fit on this curve. But then again, it kind of sucks. It's kind of slow. So we do conjecture that the optimal gate set will have this anti-commutation fraction being uniform, and it should be around 0.7. So yeah, and it's an open question, which is how can we systematically construct sets of polys which are universal, meaning you can generate all polys using commutators, and they have this anti-commutation fraction of this magic number 0.7. If you're able to systematically construct such a set for all number of qubits, that, at least in this context, gives you a way to get the optimal universal gate set, the most efficient universal gate set possible. So we don't know how to do this yet. We have some ideas, but I'm very happy to chat about whether or not this is possible. Okay, so let me end quickly by stepping back again and telling what this has to do with fault tolerance and error correction, because you might not care about these random polystrings being your universal gate sets, but I think these insights are useful even more generally. And so remember what I said the whole time we've been talking about taking a sequence of commutators of polys. And when we step back to the actual computation, what that means is that I can get a rotation about a poly Q by taking a sequence of these rotations of my generating polys. And these rotations have a very special form. Namely, the one in the middle has this angle theta, but all the other ones have angle pi over 4. And a pi over 4 rotation about a Pauli operator is, again, one of these Clifford gates. And so every time I've talked about trying to find a sequence of polys to reach some target poly, this directly translates into finding a sequence of Clifford gates that maps one poly onto another. And this is an extremely relevant problem in quantum computation, because, for example, if we want to do some, Z, 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 Z rotation of 4 qubits, which appears all the time, especially in things like quantum chemistry algorithms, the way we would normally do it is we would do a Z rotation here, and we would conjugate it by these C0 gates, which are polys, which will kind of grow this Z into a big part of 4 Zs. And what I'm saying here is that if, rather than considering these boring C0 Clifford operators, you consider Clifford operators which are generated by these long Pauli strings as kind of your basic pieces, then you can potentially kind of simplify this compilation step where you're able to, get this operator that you want with fewer elementary gates. And so again, you might say, okay, but I don't have these big Pauli string rotations. I have C0s. So why do I care about this? But that might not always be the case, because we're currently at a point where everyone is trying out all these different quantum error correction codes. And like I said, each one has a different set of gates that it is good at, a different set of Clifford gates that it can do naturally. And especially these kind of high rate codes where you have lots of logical qubits stuffed inside of one code, you don't always get a C0 between all pairs of logical qubits. You can't always do that. You get some other set of Clifford gates. And it might look something more like the one on the right. And so this kind of points towards coming up with more efficient schemes of fault tolerance, more efficient schemes of error correction, where you have these unusual Clifford gates. Because as I've shown, certain, we've shown how you can design these sets of Paulis to have the minimal size of 2k plus 1. So we need fewer total Clifford gates in order to be able to do our computation. And if we pick a set which generates more efficiently, like I talked about earlier, then we see that, in that case, we can expect to need fewer Clifford gates in our circuits in general, assuming that kind of these Clifford gates are the basic ones we have available in our error correction code. So this kind of calls for a co-design of universal gate sets in quantum error correction codes. Okay, so that brings me to the end. And I just want to summarize. I talked about this idea of having a set of Pauli strings and trying to generate other Pauli strings using commutators. And this is the question you have to answer when you want to understand, is a set of rotations generated by Paulis universal or not? So we gave a sufficient condition for this universality. We gave an efficient compilation algorithm, which is how do you target a given unitary using these kind of rotations. We showed that the minimal size of a universal set is 2n plus 1. So I've been saying 2k plus 1 throughout. And we've shown how some of these sets are more efficient than others. And we've given some ideas of how to generate these more efficient sets. Kind of maybe wrapping back to the start, remarkably, this weird fractal set of Paulis that came from this weird MBQC scheme I talked about is universal. It's efficiently compilable. It has the minimal size, and it's almost maximally efficient. So it's very interesting that this bizarre example that I came across is like almost maximal kind of in all these factors. So that's all I want to say. Thanks a lot for your attention.
Yeah, thank you, David. Yeah, it's a very interesting story. Yeah, a very nice result. Yeah.
Thank you.
Yeah. So here I have two quick questions. Say the first one for the fractal structure on the on this page. So
Yep.
on the left side, the black region.
Yes.
Can we say, like in practice, simply delete this part?
Yeah, I mean, this is this black part is just saying that the gates corresponding to these columns do not act on the higher qubits. So like kind of, this column does not act on qubits, 3 through 29. It only acts on the first two. And so if you want to ever act on, qubit 29, you're going to have to use one of these guys instead, which actually have action on it. So yeah, these dark parts just show that, the Pauli string is the identity there, so it has no effect there. And
Yeah.
so this is,
Yeah, I mean, this is in the MBQC picture, right? So yeah. So on the first hand, we have a 2D cluster state, right? And then, I mean, for as a first stage, can we, simply just not prepare this part?
I see your question. So this two-dimensional structure does not correspond to the two-dimensional space of the cluster state. So like this horizontal dimension does indeed correspond with one dimension of the cluster state, but the vertical dimension is kind of indexing my virtual qubits on which I'm doing a computation. And so, what this plot says is that if I measure, the 28th qubit on the top row, then it's going to do this big rotation on all of my encoded qubits. So like, this dark spot does not correspond to a physical qubit of the 2D cluster state. It corresponds to, it's
On a logical level, you mean? Okay.
Yeah. This y-axis is indexing the logical qubits.
Oh, okay. So, regarding fault tolerance, say, if there's some noise, or error in the black region, kind of spread out.
Yeah, again, I mean, I guess that could mean like if I'm trying to do, if I'm trying to implement a gate corresponding to one of these columns, which in an ideal noiseless case does nothing in this black region. But if there's some noise here and it does something, is that kind of what you're saying?
Yeah, does it we will spread out?
Yeah, I think it will spread out. It will, but I think this is no different from the standard setting of fault tolerance and error correction. I mean, yeah, you can have some noise in your gates and your code has to deal with it. I don't think this kind of fractal structure changes that story at all.
Yeah, another thing is, say you are using like this long string of this kind of a non-local gates, right?
Yes.
And these gates fill in the whole space of the group much more faster, right?
Yep.
So, but for tolerance, I mean, these kind of gates also spread out noise faster, right?
I see.
Yeah.
Yeah. Okay. I see. Thank you. Yes, that's true. And I think that will mostly come down to it'll be much harder to design a decoder of your code because of this spreading. You can't do kind of like a minimum weight perfect matching thing, which assumes errors kind of spread slowly and locally.
Yeah.
So yes, if this really was
Yeah, somehow it's a question about the robustness of this fractal structure. Yeah. So how a local noise affect the shape of the fractal.
Yeah, I think it will, and it will mean error correction will look a little different than if you had kind of the standard gate set.
Yeah. But anyway, this is a very interesting model. Yeah. So it's not purely like MPQC. It's more like a QCA, right? Cell automata stuff.
Yeah, exactly. I called it a MBQC kind of in 1D, but
Yeah.
I think it's some sort of hybrid thing because like in MBQC, kind of all both your space and time dimensions become space, right? But
Yeah.
in my model, space and time are exchanged in some sense.
Yeah. Okay. Nice. So okay, and because time limited, and also I think if there are questions, you can contact David directly and read his paper. He has made a paper on this topic, and I think yeah. So we thank David again, and I will chat with you a few words later. Yeah,
Okay,
and
thanks a lot.
yeah, thanks co-share. And thank all the audience. Yeah.
Thanks a lot.
Okay. Have a
See you
nice
later.
day. So we end this meeting. Yeah.